Hello. So in our first video today, I want to talk about the fundamental theorem of arithmetic. So let's jump right to it. Okay, so the fundamental theorem of arithmetic is about prime factorization. So let me define what that is first. So if you have a number n, that's written as the product of different primes. So pi's are different primes, p1 through pk. And EIs are exponents to those prime numbers. And these exponents are sometimes called multiplicity of that prime. So you're writing numbers as like a product of a whole bunch of different primes. And exponents is also like products, right? If it's 5 to the third power, you're multiplying 5 3 times. So when you write a number that way, we say it's a prime factorization. Example of it is here. So the number 1001, if you look at different prime numbers that kind of divide into it, you'll quickly discover that 7 divides into it, 11 does, and 13 does, and only one time each. If you multiply those things together, you get back 1001. So that's an example, prime factorization of 1001. So let's state the fundamental theorem of arithmetic. Every integer n has a prime factorization. So there exists a way to write it as product of primes. And not only that, there's only one way to do it. It's unique up to reordering of prime factors. So if you put like a restriction on the ordering, so for example, just put the prime in increasing order from smallest prime to be P1 and so on, then there's only one way to write a number in this prime factorization. So it's unique. It's an existence and uniqueness type of theorem. So let's prove it. So we're gonna prove this theorem using strong induction on n. So we're using strong induction, so that means that what we're gonna do is we're gonna assume that all the numbers up to n has a prime factorization that's unique. And then for n, we're gonna break it down into a smaller number prime factorization, and we're gonna solve the problem that way. Breaking it down to smaller pieces is a strong induction approach. Okay, so let's do it with the base type. The base type is a little bit weird. So the natural number 1, empty product is 1. So if you don't multiply any prime numbers, then you just get 1, because 1 is the default number if you don't multiply anything. As soon as you multiply any prime numbers into it, the smallest prime number is 2, so you're going to get some number that's larger than 1. So there's really only one way to get 1, and that's to not multiply anything, empty product. Okay, so it exists and it's unique. Let's move on to the induction step. So let's look at a number that's greater than 1. So let's first look at all the numbers that could divide into this number n. So let S be the set of positive integer greater than 1 that divides n. S has at least something in it because n itself will divide itself. So n is in S. And S is a subset of the natural numbers. So from chapter 3, we know that subsets of natural number has well-ordering property, which means there's a smallest number in that set. Whatever that smallest number, we're gonna call that element P. P is suggested because I'm gonna claim that this is a prime number, and it should be because P must be prime. If it wasn't prime, then it's a composite. So two different numbers could multiply to get p, but those numbers are smaller, and if it divides p, then it also divides the larger n. So it should have been in the set S to begin with. So since you can't go down any smaller, p has to be a prime number. Okay, by the proposition we proved last time on Monday, you could factor n into p and n divided by p, two factors. So p is a prime number, and n over p is some factor that's smaller than n. So by the strong induction hypothesis, n over p, which is smaller than n, has to have a unique prime factorization. So we broke it down into something smaller. Hence, there really exists one prime factorization of n. And that is basically looking at the prime factorization of n over p and increasing the multiplicity of p by 1, because you're also multiplying by a p to that. And if p wasn't in the prime factorization of n over p, then you have a new prime that you throw it in there. But there's only really one way to increase that. So I hope that made sense. That proves that every natural number has a unique prime factorization. So maybe you knew this already, maybe you didn't, maybe you didn't even know that this needed to be proved. But this really shows that prime numbers are really the fundamental building block of any natural number. I kind of want to think of it as like, it's like every natural number is like a chemical, and chemicals are built up of different elements that have certain bonds together, and those elements are the prime numbers. So every number has a unique combination of these primes, and it is the only combination that works to get that natural number. So it's kind of like the table of elements, right? Prime numbers are really building up everything else. So you might think that's obvious, but actually, in some number systems, this kind of thing doesn't hold. So it really lets us know that prime numbers are the things to pay attention to. Anyways, I will end the video here, and we'll talk about Euler's algorithm next time.